Hello and welcome. Today we'll be hitting Section 205 Solutions by Substitutions. And there's basically going to be three types of substitutions they show us in this section. So the first one we use on homogeneous equations. This one has a different definition for homogeneity than what we saw earlier in chapter 2. I know apparently the people naming everything didn't think diffie-q was challenging or confusing enough at times, so we'll talk about the form that we'll see them in. So m of xy times dx plus n of xy times dy equals 0. So we've seen this form before. To check if it's homogeneous, the bar that it has to clear, m of tx, ty, we have to be able to turn that into t to the alpha times m of xy, and n of tx, ty, we have to be able to turn that into t to the alpha by n of xy. And here's the key. It's not a coincidence that I use alpha for one and alpha for the other instead of alpha for one and say beta for the other. They have to equal. Alphas are equal. Very messy apostrophe s there, sorry. Alphas are equal to each other. So that's the first bar we have to clear. We just make sure that it is indeed a homogeneous equation. Once we establish that, we're free to use one of two substitutions, either y equals u times x or x equals v times y. We can use either one of them, and then of course dy, then you're just using product rule. So u prime times x or x du plus keep the u and differentiate x, u dx. If we subbed out the x's instead, then x is equal to y dv plus v dy. So product rule again. So after that, we just gotta do a little rearranging, and we have something that hopefully is an easier to work with differential equation. Solve it and then substitute. So this one we'll look at y natural log of y minus y natural log x minus y times dx plus x times dy is equal to 0. And we'll even do a little initial condition 1 on this. Y of e is 1. All right, so first I'll find m t of x, t of y. I'm going to go ahead and factor that y out. Each one of these had a y, so we have ty times natural log of ty minus natural log of tx minus ty, and we have to be able to get that back to the original. So one thing we can do here using properties of logarithms, hang on to your ty for a moment. We have natural log t plus natural log y and then minus natural log t natural log y minus ty. So log of a product becomes a sum. This became a sum, and I distributed the negative. So notice that these natural log t's will bail. And my apologies, this should be, if I factor the y, this is a -1. My apologies for the error there. So this guy is a -1 there. So then this is t times, if I distribute the y, we have y natural log y minus y natural log x. And then now that I've corrected this to be the -1 that was supposed to be there in the first place, minus y, and that is indeed t times m of xy. So here alpha is worth 1, and as long as that's the case with our n of xy, n of xy is going to be a whole lot shorter than that. N of, my apologies, tx ty is worth tx, which is t times n of xy. And here then alpha is 1. I didn't pull out a t squared or a t cubed or a t to the 1/3. So those two match. Alpha equals 1 on both. They're equal. We're good to go. So we pick out a substitution that we want to do. So one thing that you may notice is that our one term will turn into two terms when we do the substitution, as far as, there should be a dx there, my apologies. One term will turn into two terms. Since I don't really feel like doing 3 terms by 2 terms, we'll go ahead and swap out the y's then. So we'll use y equals u times x, which means dy is, use the product rule, x du plus u dx. So we're going back to the original differential equation. We're swapping out all of our y's and our dy's. So here we have a y. We'll turn that into ux. There's another y. Turn it into ux. Minus, there's another y, ux again. Natural log x. Minus, there's another y, another ux. Times dx plus x times dy is now replaced with x du plus u dx. And we're still equal to, of course, 0 on the other side. Okay, a little bit of distributing. So we have ux natural log of ux minus ux natural log x minus ux, and each of these has now a dx attached. Then we have plus x squared du plus ux dx is equal to 0. And then we get some cancellation happens. A nice pretty cancellation. So we have minus ux natural log of x dx and ux natural log ux minus ux natural log of x, and minus ux dx, and we have plus ux dx and plus x squared du. So a little bit of cancellation there. Now I'm going to kind of just regroup, put my dx is in one pile, my du is in another pile. So let's see, our dx's that survived. We have ux, natural log of ux, dx. Now we'll make it one big pile. We'll put the dx at the end. Minus ux, natural log x. And then we have, let's see, so we use this guy and this guy. Then we have plus x squared du is equal to 0. So next we can use some properties of logarithms to do a little bit more simplifying. Again, we have the log of a sum, or a log of a product, which we'll turn into sums. So then we have ux natural log u plus ux natural log x. So that's just using properties of logarithms to expand this guy. He turned into those two. Then we have minus ux natural log x. All of these guys had a dx attached. Plus x squared times du is equal to 0. And notice now that we have a plus ux natural log of x and minus ux natural log of x, those guys will drop. So then our winners, once I made it through all that cancellation and expansion, we had ux natural log of u times dx plus x squared times du is equal to 0. So this one we can then just do a little separation of variables. Ux natural log u dx is worth opposite of x squared du. So we'll divide by x squared. So we have 1 over x dx. We'll divide by u natural log u. So we have 1 over u natural log u times du. And we'll keep the negative on this side. Okay, so now we are ready to start integrating this thing. Over here, we're going to need a little bit of substitution. U equal natural log of u. We can't use u equals u. We'll use w. Let w equal natural log of u. dw then is 1 over u times du. So we basically have opposite of integral of 1 over u du. So 1 over x dx, we're going to integrate that. So equal to integral of negative 1 over u natural log u du. So we basically have a case of negative 1 over w dw. So we have natural log of x is worth opposite of natural log of w. W is natural log of u, so we have natural log of a natural log. So natural log of u plus some arbitrary constant. So from here, just for ease of calculation, this side's a little bit on the messy side. I'm going to move the constant over to the other side. So then we'll have natural log of the natural log of u is worth minus natural log of x plus some arbitrary constant. So then we can translate this from logarithmic to exponential notation. Natural log means base e. So we have e to this right-hand side, opposite of natural log of x plus c is worth the argument natural log of u. So plus e to the c, adding in the exponents, that's basically saying that we are multiplying with the same base. So this is equivalent to saying e to the minus natural log of x times e to the c is natural log of u. E to the c, we have just some other c. We can arbitrarily call it c1. So c1 e to the opposite of natural log of x is worth natural log of u. But e to the opposite of natural log of x is minus x. Or I'm sorry, x to the negative 1. We have c1 e to the natural log of x, quantity raised to the negative 1, so power to a power we multiply. That's still equal to natural log of u. E to natural log of x, x to the negative 1 is 1 over x. So we have c1 over x is natural log of u. And now we can put the original guy back in there. So recall our substitution. We let y equal u times x, so u is y over x. So c1 over x is natural log of y over x. Now recall they also did give us an initial condition. So the initial condition they gave us, let me just copy what we have over here. So we had c1 over x is worth natural log of y over x. And we had the initial condition that y of e was 1. So we can fill in what we know. So our y values are 1s, our x values are e's. So we have c1 over e is worth natural log of 1 over e. So we can get the c1 value out of this. So c1 over e is worth natural log of e to the negative 1, which then, of course, is a negative 1 on the right side. So c1 over e is worth negative 1. So c is opposite of e. So we can say our particular solution will be opposite of e over x is natural log of y over x. So this one here would be our our general solution solved implicitly. This is our explicit solution. Or my apologies, not explicit, particular solution. And in this case, we didn't do an explicit solution, but we did get a particular solution out of that. All right, so that's one type of substitution they have us do, is the homogeneous equations when we have the m of x, xy dx, n of xy dy equals 0. The next one is a different scenario and a different substitution. This is the Bernoulli equation. So the form of it, we have dy dx plus p of x times y is equal to f of x. And if we stop there, this is just your plain Jane first degree linear differential equation, but we have times y to the n. The good news is that Mr. Bernoulli was kind enough to figure out a substitution that is handy and really gets it back into a much easier to work with form and turns it back linear. And that is to let u equal y to the 1 minus n power. All right, so an example. So we'll start with x dy dx plus 6y is 3xy to the 4/3. So we're not in the right form yet, so we'll fix that. We'll divide everything through by x. So dy dx plus 6 over x times y is worth, that would be 3 times y to the 4/3 power. So now we're in the right format. Derivative plus some function of x times y to the first is worth some function times y to a power. So our substitution, u equals y to the 1 minus n. So here n is worth 4/3, so 1 minus 4/3. So our u is worth y to the negative 1/3 power. So we can also say then that y is equal to u to the negative 3rd power. Raise each side to the negative 3rd power, and you get u to the negative 3rd is y to the 1st. So our dy du would be negative 3 u to the negative 4th. And recall dy dx, if we have a u involved, would be dy du times du dx. All right, so let's continue with this. So dy dx, we can replace that. So dy du, that is negative 3 over u to the 4th times whatever du dx is worth. Then we have a plus 6 over x. There's a y. We'll replace the y by u to the negative 3rd, or just toss a u to the 3rd in the denominator. It's worth 3 times y to the 4/3. And remember, y is u to the negative 3rd. So negative 3 over u to the 4th du dx plus 6 over x u cubed is worth 3 over u to the now 4th power at the bottom. So power to a power, we multiply. Negative by a positive was a negative. That's what shipped us downstairs. And the 3's dropped out, leaving only the 4. All right, so close to a format we'd want to work with, but we've got this negative 3 and this u to the 4th. So we'll just multiply everyone by u to the 4th over negative 3. That'll give us du dx in the first one. Positive times a negative will flip this guy negative, and 6/3 is 2. We have a u to the 4th upstairs and a u cubed downstairs, so a u upstairs, and this x stays put. Other side, 3 over negative 3 is negative 1, and u to the 4th over u to the 4th is a 1. All right, I could squeeze a little more on that page. Let me just start a fresh page. So now we're looking at it with fresh eyes, as if we had just stumbled across this equation where we had du dx minus 2 over x times u is worth negative 1. This one, we can just use our integrating factor now that we're just linear. So our integrating factor, I period f period, e to the integral of this coefficient times dx. So negative 2 over x times dx. So that is e to the negative 2 integral of 1 over x dx. So that is e to the negative 2 natural log x. Excuse me. Power to a power we multiply, so e to the natural log x to the negative 2, e to the natural log of x, so this is x to the negative 2. So we have x to the negative 2 times du dx minus 2 over x times 1 over x squared times u is worth negative 1 x to the negative second. A little bit of cleanup, x to the negative second du dx minus 2 x to the negative third times u is worth negative 1 x to the negative second. So now we recognize this as a result of a product rule. So basically the idea here is we had the derivative of a product. We had an x to the negative second along with a u. If you use the product rule on that, derivative of the first part, negative 2 x to the negative third, you would keep the u. Then you would keep your x to the negative second. Derivative of u with respect to x is just du dx for now. And that's worth negative 1 x to the negative second. Now we're ready to integrate both sides. So x to the negative second times u is worth x to the negative first plus c. So multiply everything through by x squared, and u is worth x plus cx squared. Excuse me. Now we just put our original back in there. So remember, we let y equal we start with u equals y to the negative 1/3. So y to the negative 1/3 is worth x plus cx squared. If you'd like it solved for y, we can just raise both to the negative third power. So y is x plus cx squared to the negative third power. This one I don't think they gave. I don't think it gave initial conditions. Nope. So there is our, this one we were able to get all the way to an explicit solution. Although it was not a particular solution. Okay, so we're 2 of the 3 pieces in hand. Last one, we do a reduction to separation of variables. So our form, this one, if we have something of the form dy dx is equal to f of ax plus by plus c, b is non-zero, then we use u equal ax plus by plus c. All right, so an example, we'll do dy dx is 5x minus 7y over 5x minus 7y plus 4. So our u, the denominator has more stuff going on. That'll be our u. So u is 5x minus 7y plus 4. So then du dx, derivative of 5x is 5. Derivative of negative 7y is negative 7 times dy dx. And derivative of a constant is, of course, 0. Well, one useful substitution I see with that is I have a dy dx by itself. I can get a dy dx by itself with this guy. So 7 dy dx is worth 5 minus du dx. So dy dx is 5/7 minus 1/7 du dx. So now we can rewrite the left-hand side of that equation. The right-hand side as well, we can make it look like something written in terms of u's. So dy dx, that's now our 5/7 minus 1/7 du dx. Right-hand side at the bottom is just our u, 5x minus 7y, and we're missing the plus 4, so we're 4 short of what u was, so u minus 4. Okay, so let's try to get the du dx by itself. So negative 1/7 du dx is worth u minus 4 over u minus 5/7. We'll multiply everything through by a negative 7. So then du dx is worth negative 7 by u minus 4 over u minus, well, that'll turn it into then a plus 5. So negative by negative kicked us over to a positive, and the 7's dropped, leaving us just the 5. And this is a u, not a 4. I don't know why that looked like a 4 before. This is a u downstairs, so we'll make this guy 5u over u. So du dx is now negative 7u plus 28 plus 5u over u. So du dx is worth 28 minus 2u over u. So here we can now do the separation of variables, get all of our u's on one side, all of our x's on the other. So we have u du over 28 minus 2u is worth dx. Let me pick it up from the other. So we have now a fraction. We can just use long division. Let me just copy what we had on the other page there. U over 28 minus 2u du was worth dx. So we'll do a little long division here. So u plus 0 on the inside, negative 2u plus 28 on the outside. So what I would multiply u by to reach negative, or what I would multiply negative 2u by to reach positive 1u, that would be a negative 1/2. So negative 1/2 by 2u, negative 2u is u, and negative 1/2 by 28 is negative 14. We subtract them, which will flip both signs. So 14 left over. So now I can say that that's my remainder, so remainder over divisor. This is a u. I know it looks a little too much like a 0 there. So left side is now negative 1/2 plus, we can go ahead and factor a 2 top and bottom and drop that to 7 over 14 minus u times du is worth dx, and then we just integrate both sides. So integral of negative 1/2 is negative 1/2 u. Our integral of the 14 minus u all over 7, we know we'll have a 7 hanging around outside. We'll have a natural log of 14 minus u. If I did the derivative of 14 minus natural log 14 minus u, 14 minus u would be downstairs. We would also have to multiply by a negative 1, so that will flip that sign. is worth x plus some arbitrary constant. So -1/2 u minus 7 natural log of absolute of 14 minus u is worth x plus c. And then we just put the original back in. So this time our u was, recall from the other page, 5x minus 7y plus 4. So we have -1/2 of 5x minus 7y plus 4 minus 7 natural log of 14 minus 5x plus 7y minus 4. So we flipped each and every one of those signs, since it was minus the entire thing of u is worth x plus c. And really just a little cleanup inside would be sufficient. So -5/2 x plus 7/2 y minus 2 minus 7 natural log of absolute value of -5x plus 7y plus 10 is equal to x plus c. Notice this one is also a constant, so you may also see it written with that taken out. So it might also be written as -5/2 of x plus 7/2 of y minus 7 natural log absolute value of -5x plus 7y plus 10 is equal to x plus some arbitrary constant. So if you don't see the -2, don't be alarmed. They just combine that with another arbitrary constant and said, okay, here's an arbitrary constant at the end. Okay, so that was our third substitution method. So in 2.5, I would recommend 1 through 29 on the odds. If you have questions, please get in touch. Otherwise, I will see you next time. Stay safe out there, everyone.